Hello everyone, and thanks for watching Edupedia World videos. I am Manish Agrawal, and today we'll continue with the topic of mole concept. In the topic, today we'll focus upon the subsection of atomic and molecular masses. Alright, so let's begin our lecture of today. Atomic mass. Well, as the name suggests, atomic mass is nothing but mass of an atom. You already understand the word mass. Mass is nothing but a measurement or a measure of the amount of substance or the amount of matter inside a body. Okay, it can also be seen as a measure of inertia of a body. We don't have to go into the physics of it, and neither do we have to go into the difference between mass and weight. Okay, we just need to note here that when we calculate mass of atoms, the values will come out to be very small. Say mass of a person is 50 kilogram, mass of a baby might just be 5 kilogram, but atomic masses are in order of 10 to the power minus 24 grams or 10 to the power minus 27 kilograms. Alright, so this is what I meant when I said that they are very small values. So for this reason we need to define a separate scale, a separate unit of measurement to account for masses of atoms, because they are so small. So this unit is called atomic mass unit. Okay, so atomic mass, first, it is nothing but mass of an atom. Second, it is measured in terms of atomic mass unit scale, okay, and represented by AMU. Now, what do we mean by 1 AMU? That is 1 atomic mass unit. So, what do you mean by 1 kilogram? When I ask you this question, you might answer me with the standard definition of 1 kilogram from the international standards of weights and measurement. Or more commonly and or more understandable definition is 1 kilogram is a unit of measurement and it is equivalent to 1000 gram. Similarly, when I ask what do you mean by 1 gram, you might answer me by saying it is nothing but 1000 milligram or 10 to the power minus 3 kilogram. So similarly, 1 atomic mass unit is nothing but some value in grams. Okay, so I need to represent 1 AMU in terms of kilogram or gram or some other reference unit which I am already aware of. So in terms of gram, 1 AMU is defined as 1/12 the mass of one carbon 12 atom. Okay, here what I have done is I have taken one atom of carbon, and this carbon atom must be the isotope carbon 12, not carbon 13 or carbon 14. Okay, so this you have to assume to be true, because this is what is the international accepted standard right now, that we take one atom of carbon 12 and we calculate its mass. Now divide that mass by 12. So the value which you get is the value of 1 AMU in grams, and this value comes out to be 1.66 into 10 to the power minus 24 gram. So now you can see how small the value of atomic mass unit scale is. It is 1.66 into 10 to the power minus 24 gram. In kilogram it will be 1.66 into 10 to the power minus 27 kilogram. That is why we need a different scale for measuring masses of atoms. Okay. So now you know what 1 AMU is. You need to see here that this value is nothing but similar to what you already know about masses and their units, like 1 kilogram, 1 gram, 1 milligram, 1 microgram, okay, or 1 pound, okay, or any other unit that you might know. Okay, this is just another unit to calculate mass. You need not confuse it with some new phenomena or new concept. Alright, 1 AMU is nothing but 1.66 into 10 to the power minus 24 grams. Okay, just remember this value, and you have to remember this conversion value because it might or might not be given in your questions. So now we know what 1 AMU is. You also need to note here that the atomic mass can also be measured in Dalton or unified mass. The Dalton is not used anymore. Okay, the unit Dalton represented by capital D small a dA is not used anymore, and unified mass is what is now used in the present world. Okay, so one atomic mass unit AMU has been replaced by unified mass, that is U, and 1 Dalton is equal to 1 AMU is equal to 1 unified mass. Okay, in terms of conversion, they all three units are equivalent. It's just a way of representation. 1 Dalton was the unit used initially. After that, 1 AMU was being used, and now both of them have been replaced by unified mass, and now we only say 1 U. Okay, so 1 U is nothing but 1.66 into 10 to the power minus 24 gram. So when you have an atom of nitrogen and I ask what is the mass of nitrogen, so you will represent it in terms of unified mass. So one atom of nitrogen weighs 14 U or 14 unified mass. Alright, so when I say 14 U, I mean 14 into 1.66 into 10 to the power minus 24 gram, or 14 multiplied by 1.66 into 10 to the power minus 27 kilogram. Okay, similarly I can have an oxygen atom. An oxygen atom has atomic mass of 16 U. Okay, one single atom of oxygen has mass of 16 U, that is again 16 into the conversion formula 1.66 into 10 to the power minus 24 gram. Okay, so you have to remember this conversion value. Just like you have remembered 1 kilogram is 1000 gram, you have to now remember 1 AMU is 1.66 into 10 to the power minus 24 gram. Alright, so now we know what atomic mass is. Let's move on to molecular mass. What do we mean by molecular mass? Just like atomic mass was mass of an atom, molecular mass is nothing but mass of a molecule. Okay, so it is again measured in terms of either AMU or U or Dalton. Alright, so the currently accepted unit is unified mass, that is U. Okay, so mass of one molecule of a compound in AMU or U is called molecular mass. So you take any compound, let's say water, and we take one molecule of water, we calculate the mass of that one single molecule, and that will be the molecular mass of water. So to calculate, you have to follow certain steps. Okay, unless you already might know how to calculate molecular mass, it's a pretty simple thing and you have already studied it in class 9th. Okay, but let's go through it again. So to calculate molecular mass, first step that you need to do is write the molecular formula itself. Okay, you already know what molecular formula is. We covered it in our basic concepts. Molecular formula, for example, we took glucose C6H12O6. Okay, we said molecular formula shows the atoms, the various different atoms or different elements which have come together to form the molecule. So here in glucose there was CH and O, C6H12O6. The subscript, the whole number subscript 6, 12 and 6 represents the exact number of atom of each element which have combined to form the molecule. So molecular formula. So you have to write that molecular formula. Okay, once you have written down the molecular formula for which you have to calculate the molecular mass, note down the number of atoms of each kind and their respective atomic masses. Alright, so we have here carbon, hydrogen, oxygen. We'll note down their atomic masses, and then we'll multiply number of atoms of each kind with the corresponding atomic mass of that atom. Okay, and in the last step we just need to sum up the products of, that is the products, the multiplication answer we obtained in step 3 needs to be added up to arrive at the final molecular mass. Let's look at some examples for calculating molecular mass. Say we talked about glucose, so let's take glucose C6H12O6. So I have carbon, I have hydrogen, and I have oxygen. So I have identified the three elements involved in the molecule of glucose. Now atomic mass of carbon is 12U, atomic mass of hydrogen is 1U, and atomic mass of oxygen is 16U. Now you don't have to worry about remembering this information. This is usually given in your questions. Okay, and some of the common values, like for carbon, hydrogen, oxygen, the atomic mass values is quite common, and you will eventually come across them so many times that you will end up remembering them anyway. Okay, so these are the elements which are there in the molecule. These are atomic masses of the elements. Okay, so we have noted this down. In step 2, what we do is we note down the number of atoms as well, number of atoms of each kind. So carbon, number of carbon atoms were 6, number of hydrogen atoms were 12, and number of oxygen atoms were 6. So I have atomic mass of each atom and the number of those atoms. Okay, so in the third step, what I do is I multiply this. Alright, so I have 6 carbon atoms in the molecule, and each carbon atoms weigh 12U. Alright, so each carbon atom weighs 12U, and I have 6 such atoms. So what is the total weight of carbon atoms in the molecule? 12 into 6. Alright, it is 12 into 6. Similarly, I have 12 atoms of hydrogen, each weighing 1U. So total weight of hydrogen atoms in the molecule is 1 into 12. Similarly, total weight of oxygen is 16 into 6. Alright, so you write the products. Okay, this will be 96. Now in the last step, what you do is you add up these values. So what I do is I add 72U plus 12U plus 96U. What I'll get in the end will represent molecular mass of glucose. Okay, so molecular mass of glucose is nothing but 72 plus 12 plus 96U. Okay, and what would the answer be? Let's calculate 84 plus 96. So the answer is 180. Yes, so mass of one molecule of glucose is 180U or 180 AMU or 180 Dalton. Alright, so now we know how to calculate molecular mass. Similarly, you can have ammonia. Okay, now let's do it very quickly, not in the same elaborate way we did above. Okay, we already know that it will be given in the question, or you will eventually remember this value, that one nitrogen atom weighs 14U and hydrogen atom weighs 1U. This means molecular mass of ammonia, alright, molecular mass of ammonia is nothing but 14 plus 3 into 1U, because there are 3 atoms of hydrogen, that is 17U. Okay, so if someone asks me molecular mass of ammonia in grams, it is 17 multiplied by 1.6 approximately into 10 to the power minus 24 gram. Okay, I have approximated. You can use a more accurate value, 1.66. Even 1.66 is actually approximate value. So 17 into 1.66 in SI unit, it will be 10 to the power minus 27 kilogram. So SI unit of atomic and molecular mass is still kilogram, and CGS unit is gram. The AMU or U or Dalton is just a more commonly used unit, because it is more convenient, because the values are so very small. Okay, so the SI unit, again SI unit will remain to be kilogram, and CGS unit of atomic and molecular masses remains to be gram. So let's move back to our theory of atomic and molecular mass. So Next point that you need to study is relative atomic mass. Now this is a pretty simple concept. It might sound confusing, but it's quite theoretical. You won't actually need to use this much in your questions. Alright. So relative atomic mass is nothing but, as the name suggests, relative. It is atomic mass of an atom of one element with respect to atomic mass of an atom of another element. Alright. So what you do is you take a reference atom. Okay. You take a reference atom and you calculate its atomic mass, and then you calculate atomic mass of other elements with respect to that reference atom. What you get in that case is relative atomic mass. Okay. So what we get in that case is relative atomic mass. So let's say I have an oxygen atom. Okay, relative atomic mass is nothing but mass of one atom with respect to mass of another atom, which will be the reference atom. Alright. So how do we take this reference atom? Well, initially the reference atom was always taken to be hydrogen because it is the lightest element. Alright. So mass of one atom divided by mass of one atom of hydrogen. But the problem was this value, the hydrogen atomic mass, was stopped being taken as the reference value. Instead of that, people shifted to taking oxygen as the reference atom, and now we take carbon as the reference atom. Okay. So whereas mass of hydrogen was 1 U, but the mass of oxygen is approximately 16 U and that of carbon is approximately 12 U. So to still arrive at the same values of relative atomic masses, what we now do is we calculate mass of one atom and we divided it by 1/12 the mass of carbon 12 atom. Okay. Before this, what they did was, before this they took mass of one atom and they divided it by 1/16 mass of oxygen 16 atom. Alright. And even before that, what we simply did was mass of one atom divided by mass of one hydrogen atom. Okay. Now mass of one hydrogen atom comes out to be approximately 1 AMU. Okay. Mass of one hydrogen atoms comes out to be 1 AMU or 1 U. So relative atomic mass is nothing but mass of one atom divided by 1 U. Okay. So you get what I am trying to say here. So to move from here, to move from this, so to move from this to this, alright, what they did was they divided the denominator by respective atomic mass of the reference element. So now you know this. Let's see how do we calculate relative atomic mass of an element. So I have to calculate relative atomic mass of nitrogen. So I already know atomic mass of nitrogen is 14 U. Okay. So relative atomic mass will be 14 U. Okay. This 14 U divided by 1/12 mass of one carbon 12 atom. One carbon 12 atom weighs 12 U. Okay, mass of one carbon 12 atom is 12U. So relative atomic mass is 14U divided by 1U, that is 14. Okay, so relative atomic mass is nothing but same as atomic mass in magnitude. Alright, so relative atomic mass is nothing but same as atomic mass in terms of magnitude. The atomic mass of nitrogen was 14U. Alright, atomic mass of nitrogen was 14U and relative atomic mass came out to be 14. So the only difference is of unit. Atomic mass will have unit of U, whereas relative atomic mass will be dimensionless. It is a ratio, so it cannot have a unit, it cannot have a dimension. Okay. So this is what we mean by relative atomic mass. You don't actually need to calculate it in the questions, but you need to be aware of the concept, because in most of the text the atomic masses which are given are actually relative atomic masses. Okay. Why? Because this is how we started first. One reason is this is how we started measuring the atomic masses initially. We didn't have good weighing machines, alright, very accurate, very sensitive weighing machines back then. So what scientists did was they took one atom, that is one atom of one element, and they measured masses of each element with respect to that certain one atom, with respect to that reference atom. Okay. So this is still one of the best way of representing atomic masses. Okay, because in that case you don't actually have to worry about the decimals, or you don't actually have to worry about an absolute frame of reference. Okay. So you don't need to go into all those details. You just need to remember relative atomic mass is nothing but same as atomic mass without the dimensions or without the units, right? So let's move on to our next point, which is average atomic mass. Now this again, this is what is mostly a theoretical concept, but it is very important, because again the average atomic mass is what we normally used in our study of chemistry. So let's see what we mean by average atomic mass. So you have already heard the term isotope, alright. In today's session, even in the previous two sessions, we have come across the term isotopes time and again. Though we'll study them in detail in atomic structure, we know that hydrogen has isotope deuterium and tritium, alright, each having different atomic mass. Hydrogen atom with atomic mass 1, deuterium with 2, and tritium with 3. Similarly, we know that carbon has various isotopes. Okay, carbon has isotope 12, 13 and 14, and similarly oxygen can have various isotopes, let's say 16 and 18. Okay, so when I say carbon 12, I mean the isotope with atomic mass 12U. When I say carbon 13, I mean the isotope of carbon with atomic mass 13U, and lastly the one with 14U. Similarly, I mean here that oxygen 18 is nothing but isotope of oxygen with atomic mass 18U, and here it is isotope of oxygen with atomic mass 16U. So since most elements, in fact, a lot of elements have different isotopes found in nature, okay, on our very earth, carbon has 3 different isotopes. So how do I actually calculate atomic mass of carbon? How do I understand whether you mean carbon 12, carbon 13 or carbon 14? So there are two things we need to note here. First, we usually take into account the one which is in most abundance. So carbon 12, for example, has 98% abundance out of all carbon isotopes, whereas carbon 13 and 14 are approximately 1 and 1%. Actually the values are different, but let's assume for our purposes that carbon 12 occupies 98% of all carbon atoms in the world, and carbon 13 and 14 only occupy 1 and 1%. Okay. So one way is to just approximate all carbon atoms to be carbon 12, because they are in so much abundance, they are basically found everywhere. Alright, or a better technique is just to take the average of these three values. Okay, the average of these values, and then use that average value for all our purposes. And this is what scientists usually do. This is what we'll do in chemistry. In fact, the atomic masses which are given in your textbook are average atomic masses. All right, the textbook people have already calculated these averages, okay, or have taken them from reference table uh, with various scientific communities, and directly use them in your textbook, okay, without going into details how these averages were calculated. So here we are going to study how these average atomic masses are calculated. Okay, so let's take the example of carbon 12. All right, so we already seen that carbon 12 is formed with 98%, okay, with 98% abundance. Carbon 13 is found with 1%, and carbon 14 is again found with 1% abundance. Alright, so for example, if I have total 100 atoms of carbon, out of these 100 atoms I can expect that 98 atoms will be carbon 12, 1 atom will be carbon 13, and 1 atom will be carbon 14. So how do you calculate the average? Okay, you have already done this since childhood. How do we calculate average? So here atomic mass is not just atomic mass, it is actually average atomic mass, is equal to, you sum up all the values and you divide by total number of values. Alright, so what we do is we sum up all the values, summation divided by total number of values. Okay, this is what we mean by average. So let's sum up all the values. So I have 98 atoms, each weighing 12 U. So 12 U into 98. Then I have one atom weighing 13 U. Okay, and then I have another atom weighing 14 U. In all, total number of atoms present with me are 98 plus 1 plus 1, that is 100. Okay, so what I have done is I have simply multiplied the atomic masses with their respective abundance. Alright, the carbon 12 atom, the carbon 12 isotope had an abundance of 98% or 0.98 in terms of fraction, plus, okay, this is plus carbon 13 has an abundance of 1%, that is 0.01. Similarly, carbon 14 is assumed to have an abundance of 1%. So this value, this summation would give me the average atomic mass of carbon 12, and this summation comes out to be equals to approximately 12.03 U or something like that. Alright, so that is why we assume the mass of, or atomic mass of, carbon atom to be 12 U. So similarly, the atomic masses of each element of oxygen, nitrogen, chlorine, they are all actually average atomic masses calculated in this method using the percentage abundance or percentage values present on earth of their isotopes. Alright, so let's see what average atomic mass is. They are nothing but average of atomic masses of isotopes of an element. Alright, now lastly we need to look upon formula mass. Now this is nothing new. Formula mass is nothing but molecular mass. Okay, so why do we use the term formula mass instead of molecular mass? Well, it is done so for ionic compounds. Alright, for ionic compounds we use the term formula mass instead of molecular mass. Why? Because ionic compounds are not actually present in terms of molecule. For example, if I have NaCl, alright, NaCl is an ionic compound. So in nature, the solid NaCl, okay, you have a block of solid NaCl, that is salt, okay, table salt. So it is not actually present as, say, an atom of Na combined with an atom of Cl in form of a molecule. Alright, so NaCl is not present in this way. That is why we cannot call NaCl molecule as having independent existence. And since the NaCl molecule does not have independent existence, it is technically wrong to refer to its mass, that is molecular mass. So instead of that, what we have is the NaCl is found in terms of this, that Na positive, and at some distance you have Cl negative, then again Na positive, and then again you have at some distance Cl negative. So this is pretty much true for all ionic compounds. Alright, in ionic compounds there is no existence of this individual entity NaCl molecule. What you actually have is, you have a crystalline structure with positive and negative ions present at different vertices or locations in the structure, and hence instead of referring their molecule as molecular mass, instead of referring to the mass of their molecule as molecular mass, what we do is we refer to their formula. Alright, NaCl is still represented as NaCl, though the molecule NaCl does not exist. The formula for sodium chloride will be NaCl, and hence we call it as formula mass and not molecular mass. Okay, and again the method for calculating is still the same. What you do is you take atomic mass of each of the constituting element. Atomic mass of sodium is 23, atomic mass of chlorine is 35.5 U. So what you do to calculate formula mass, okay, to calculate formula mass of NaCl, what we do is we add the two values. We add 23 with 35.5. What we get is 58.5. Alright, what we get is 58.5 U. So this is the formula mass of NaCl. At many places you will find the term molecular mass instead of formula mass, so don't be confused, they are the same thing. But if you want to go into technical details, then for ionic compounds the term molecular mass is replaced by formula mass. Otherwise they mean the same thing, they are similar. Okay, so it is only used for molecular mass of ionic compounds. So until next time, and once again thanks for watching Edupedia World videos.